ones that we had done the other day. So here's what I'd like you to do. Let's plot an A triple prime at -3/2, 5/2. A B triple prime at -3/2, 3/2. And then C triple prime at -3/2, 0. So if I go over 1.5 and up 2.5, there would be my A, there would be my B, and there would be my C. And we'll call that figure D, even though it's so little itty bitty, I can't really tell. Okay, so first question. Is this an dilation, a reduction or enlargement? Reduction, because it's getting smaller. Perfect. And what we want to do, our goal is we want to find the scale factor of the dilation. Okay. What's the definition of a scale factor? Yes, but how do you find it? It is the amount it goes up or down by, but how do you find what the scale factor is? That means you need the actual kind of more specific definition. Anybody remember the actual definition? Yes, which is called a what? It's not a division problem, it's a, what's another word for a fraction? Ratio, perfect. It's a ratio of two corresponding sides. Okay, so to find my scale factor, then what I need to do is look at my ratio and the two corresponding sides. So, first off, since it's a reduction, well, which one do you want to go from? A, B, or C? You want to do C? Okay, so we're going to do a dilation of C. We don't know what the scale factor is. I know it's going to be about the origin. And it'll be from A double prime, B. Okay, so there's my notation. I'm getting it all set up. All I got to do is find the scale factor, right? Okay, so if it's going to be a reduction, is my scale factor going to be larger or smaller than 1? Smaller, right? A reduction has to be smaller than 1. Okay, and so I'm finding from D to C. Would you agree with that part? Okay. All right, so all you need to do is count the length of a straight side. Okay? So from here to here, it's 1. When I look from here to here, I have, because that's my corresponding side, right? I have 1, 2, 3, 4. So my scale factor is 1/4. All right? Does that make sense? Yes? All right. Then that was just a little recap of what we had done the other day, yesterday, Friday, whatever. There's some of those for you to practice creating a new dilation. And so now let's take a look at the next one. All right, everybody got this out? We ready to roll? Yay? Okay. So when we were doing dilation up here, we were multiplying it by 3/2. So we took each coordinate point and we multiply it by the enlargement, correct?
Correct.
Okay, so what if we don't have an ordered pair? What if we just have side lengths of 2, 6, and 8? Okay, then it's going to be enlarged by a scale factor of 4. How do I go about doing that? How do I find the new side lengths? Multiplying by 4, absolutely. So if I have one side length of 2, one side length of 6, and one by 8, I multiply each of them by 4. That means I'm going to have a side length of 8, a side length of 24, and a side length of 32. Easy peasy, huh? Okay. All right. Coca-Cola wants to advertise Diet Coke on a billboard. I mean, this is like this stuff's true. And the only difference is that when they go to do the graphics for it, they have to, the pixels, how much your graphics are pixelated depends on, how blurry it is when you blow it up and stuff. That's what you do when you're doing the graphics. You take your scale factor and multiply your pixels by it to see, and if it's over a certain number, then it's going to be too blurry kind of thing. So, all right, anyway, so we have an image of a bottle that's 10 feet tall. That's how big my billboard's going to be. The original bottle is 10 inches. What scale factor will they use for the advertisement? So, first question, enlargement or reduction?
Enlargement.
It's going to be an enlargement. Okay, and so what's my scale factor have to be greater than? So it's got to be greater than 1. Okay, so I'm going to do the billboard over the bottle for my ratio. So then I have 10 feet to 10 inches. Why is it 12? Because you got to convert both so that you're in the same unit, must have the same unit of measurement. So if I multiply both 12 inches to 1 foot, that gives me 120 inches for every 10 inches. So I have a scale factor of 12. You guys, put your phones away. All right, good so far? Okie dokie. Dilated image, some true or false. Corresponding angles are always congruent. True or false?
True.
Why? Why? Prove it to me.
Because the angles are the same.
How do you know the angles are the same? Duh, that doesn't prove it. That just says it's a true or false. Prove it. Give me a reason why you know that the corresponding angles are always congruent.
The shape has to stay the same. The angles.
How do you know though?
Because you can only have so many degrees now.
Yeah, but I can still I mean, I can have different angles. How do you know a dilation has congruent corresponding angles?
That's a good shape.
Oh, because the size.
Because, wait, what did you say? Alan, what'd you say?
It doesn't change the shape.
Which makes it what? They're similar. Okay? So, dilations are similar figures. And so, all the angles are congruent. Okay? Basically, by definition of similar figures. Okay, good. All right, corresponding side lengths are always congruent. True or false? What do you think?
False.
Why?
Changing the size of the side.
How, it's more specific than changing the size. I agree, but we need more specific proof. Huh? They're proportionate. Okay. Need more proof. No. Not on dilations. You can't have different angles on dilations. So that's what we just proved up here. How do you know that the corresponding side lengths are they always congruent? First of all, you said yes or no.
No.
You said no. Okay. How do you know that in regards to dilations? What are dilations?
They're changing size, but not in shape.
It changes the size by how? What'd you say, Alan? No, they're not rigid motions because then then they're the exact same in congruent triangles.
It changes size.
How does it change size? What two vocabulary words?
Changes size in proportion that have
Huh?
relation.
Yeah, they're enlargements or reductions. Okay, so your dilations are either enlargements or reductions. So they're so they're never congruent. Alrighty, next one. Corresponding side lengths are always parallel. What do you think about this one? Yes?
They're always parallel as long as there's not any other transformation.
But why?
Because there's only a change in size, not a change in orientation or location, as long as there's not another transformation.
Did you guys hear what he just said?
No.
Okay, he said, and it's easier with the visual. What he said was, it's true because because the side lengths change, but the orientation or position on the graphs don't. Huh? Except for it says as long as there's no other transformations. So if you're just doing a dilation,
This is like
no other rot.
This is no other transformations like that.
Yeah, that's just an example. So like no other, no reflection, no translation, nothing. Okay, and if you think about it, let's say we blew this up by 2. This line is going to be parallel to that line. We just made it bigger. And in fact, your scale factor, the distance between here, between the parallel lines, is going to equal your scale factor as well. Okay? All right, triangles are congruent with dilations. True or false? What?
False.
Why
Good
false?
size.
Same thing as all the other reasons up here. Okay? They're enlargement or a reduction. So they're never the same, never congruent. Okay? All right. The new figure will be scale factor times as big or small, and scale factor times as far or close. True or false? What do you think? Will the new figure be scale factor times as big or small? Yeah, that's the whole thing of a dilation, right? We agree with that one. What about scale factor times as far or close? That's how far it moves away from it when you're blowing it up. And that's your distance. And so that one's a true as well.